right. Okay, so last year, we talked about two-dimensional motion in a circle, rotational motion, and now we're talking about two-dimensional motion, or sometimes even three-dimensional motion, as something goes back and forth. It's called harmonic motion, sometimes also called periodic motion. So, what does periodic mean? You learned in chemistry what periodic means. What does periodic mean? You forgot in chemistry what periodic means. So, it used to be that when you went to the library, oh, Alyssa?
Oh, sorry, no, I'm like thinking.
Okay, so it used to be when you went to the library, you found the periodicals section, and that is where you found magazines and newspapers. Why were magazines and newspapers called periodicals?
Because they were released periodically.
Yeah.
Exactly, they were released periodically. And what does periodic mean? All week, okay. So something came out every week or every month. It happened in a pattern. The time that something happened was a pattern. And harmonic motion is also periodic motion. Harmonic motion is what you get when something happens at a regular interval in time. So the classic harmonic motion are springs and pendulums. So over here, I got my favorite pendulum. It's a softball tied to a piece of string attached to a magnet. And you know, a pendulum is something that goes back and forth and back and forth and back and forth. And if there were no friction, it would go back and forth forever. And a spring, you know, a spring is something that goes bouncy, bouncy, bounce. This is my favorite spring. It's a slinky. And if there were no friction, it would go up and down forever, which is pretty cool. Now, there's a really neat kind of pendulum that you will find in a lot of museums, a lot of science museums, called a Foucault pendulum. And a Foucault pendulum is a gigantic pendulum with like a huge metal something. Usually it's a ball, but it doesn't have to be. It's very, very heavy. And at the top there's a little motor that acts against friction, so it swings constantly. And around the Foucault pendulum, you put usually 360, sometimes 180 little pins. And as the thing swings back and forth, guess what it does? It knocks over the pins. And every 15 minutes, it knocks out a new pin. So you can basically use it to tell time. After 12 hours, it's knocked down all the pins. So the idea is the rich scientist would come in and they have their servants set up all the pins, and then it's like, what time is it? How many pins that knocked over? 4 o'clock. Okay. And then after it knocked all the pins, the servants would come set them up again. And that's how the Foucault pendulum works. It would swing back and forth while the Earth spun under it. And for some vectors I don't want to go into, it would knock down all 360 pins, 180 by 2. It would knock down all 360 pins in 12 hours. The Foucault pendulum. So if you're ever at a big science museum, they have one in Portland. I hope they have one here at the Children's Museum, but they don't have one here at the Children's Museum. But they're around.
They have something similar.
Yeah, yeah.
So
It goes back and forth, and back and forth, and back and forth, and back and forth. Kind of like if this went back and forth in a straight line for 12 hours, it would start this way, and after 6 hours, it would be swinging this way. And then after that 12 hours again, it would be back to swinging this way. Because the Earth spins under it. The Earth spins under the pendulum. So that's kind of cool. Way beyond the scope of this course is the math, but we're going to primarily focus on things that swing and bounce. Okay? So I got my spring, and it bounces, and I got my pendulum, and it swings. And we learned last time that there's a name for how long it takes to go back and forth. What's that name? Period. Okay? So the name we give for something that goes back and forth, the time for one back and forth is the period. And the inverse of the period is the what? Frequency, yeah. So period, which is capital T, is measured in seconds. Frequency, which is 1/t, is measured in per seconds. You can write it seconds to the -1, or you can write it 1/seconds. They're per seconds. So frequency is the number of back and forths you get every second. Make sense? And there is a named unit for frequency. What is the named unit for frequency? Hertz, yeah. Hertz, Hz. So the named unit for frequency is hertz. A hertz is a per second, second to the -1, or whatever. So ever been in a movie theater and you encountered that jerk who kept bouncing his knee or his leg? Like bounce, 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 and you're like, oh my gosh, you're making the whole row vibrate. You encountered that?
Yeah, I mean.
Yeah, so you'll have some guy, you'll have some guy sitting down and he's at the movie theater and he's like, and eventually the whole row starts vibrating.
That's because Rome is that guy.
Rome is that
I got
guy.
nervous.
Rome never experienced it. Rome is that guy. Well,
Rome is that one guy that can't.
when you cause something to vibrate and those vibrations add together, that has a special name and it's called resonance. And here's the cool thing. If you had a person doing this, and another person right there next to him doing the same vibration, those vibrations would add together. But if you had someone that was vibrating their leg at half that frequency, their vibrations would cancel out. Every other vibration would be canceled out by the next person. It's called mechanical resonance. You get the same thing in a trumpet, where you go and it vibrates the metal or the air in the trumpet, and that trumpet makes noise. And that's the next unit. After we talk about this, we're going to transition to vibrating air and talk about sound waves. Cool?
And then we're going to go to
Then we're going to do optics and talk about vibrating electrons. All right, so periodic motion, again, also called simple harmonic motion. So harmonic is just vibrating back and forth. So periodic motion, called simple harmonic motion, is the back and forth motion when the restoring force varies directly with the displacement from equilibrium. So there's a lot to unpack here. Restoring force sounds like what? Exactly, goes back to something, okay? So the restoring force is the going back force. So equilibrium, we learned what equilibrium is. Restoring force is the going back force. What is the equilibrium? What is equilibrium? The force that brings something to a stop, okay? When something is at equilibrium, how would you describe the forces? Equal, exactly. When something is in equilibrium, we would describe the forces as equal. They've all equaled out. For instance, who among you, with a show of hands, who among you is at equilibrium in the vertical direction? 1, 2, 3, 4, 5, 6, 7, 8, 9. So almost all of you, everybody but Thane and Charles are at equilibrium because Thane and Charles are flying off their seat or sinking into it.
You're staying in the same spot
Yeah.
vertically.
Right?
Nah.
Oh, no, Thane's also. So, yeah, if you are not flying off your seat or sinking through your seat, you are in equilibrium in the vertical direction. There is an upward butt force, or a downward butt force, and an upward chair force. Okay? And those two things are equal.
I don't like that you said, but.
Okay. Mirror race it. Ass force.
There we go.
Yeah. Okay, so there's a downward ass force and an upward, there's an upward chair force, and unless you are sinking through your chair or flying up out of it, you are at equilibrium.
Like it's.
Capiche? Verstehen?
Yes.
Comprende? Okay, so when something is in equilibrium, how do you say understand in French? Say it again. Coupongua? Coupongua. I'll get there. Okay, we'll get there. All right, so this ball right now is in equilibrium because it is neither falling off the string or being launched forward or launched up, right? Now, when I bring it away here and release it, it's not at equilibrium anymore. Because how do we know it's not in equilibrium?
It's changing vertical position as it moves in this pendulum motion.
And so I heard it's moving, so it must not be in equilibrium. Can you be in equilibrium and still be moving?
Yeah.
Yes, because you can have velocity but still have no net force. But if you have what? You don't have a net force of 0. Acceleration. Does this ball have an acceleration? Yeah. It's going faster, faster, slower, 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 faster, faster, slower, slower. You get the idea?
Yeah.
Okay? So it is going faster, slower, faster, slower. But there are 3 points where it doesn't have that acceleration. There,
and the very bottom.
there, and there. Okay? We're going to focus on the middle one. We're going to call the middle one the equilibrium position. So at the point at which it goes from faster to slower, right down here, that's equilibrium. Cool? Give me a thumbs up if this makes sense to you. All right. So equilibrium, not equilibrium. Equilibrium, equilibrium. So there's the equilibrium of a pendulum. Equilibrium of spring, a little bit easier to visualize. There's an upward force from the spring and a downward force from the weight. And if it's not moving, it's at equilibrium. Okay? The upward spring force and the downward gravity are canceled out, it's at equilibrium. Now if I bring it down here, have I changed the weight? No, I haven't. I haven't added anything. I haven't changed the weight. What I have added is what? Yeah, I basically caused this spring to pull back more. I've increased the spring force. Now if I let it go, what direction will it accelerate?
Upwards.
Up, because the net force is in what direction? It's up. So if I let it go, the acceleration is up because the net force is also up. Make sense? Yes?
Why is the net force also up? Because you're pulling it down, so it has to go to counteract that?
Yeah.
Is that what you're saying? Okay.
So I'm holding it down here. When I let go, the upward spring force will be larger than the downward weight. So the acceleration will be up,
No.
as it is. However, when it goes above the equilibrium point, something kind of interesting happens. When it goes above the equilibrium point, slow down there, spring. The restoring force, which is the spring force, is now less than weight. Does the weight change as it travels up and down?
No.
No, but the restoring force, which is what the spring is providing, does. If I bring this above the equilibrium point, and I let go, in what direction will it accelerate? Down, because there's a net force that is down. Yeah, that is down. Is it going to follow free fall?
No.
No, because the spring is still providing some sort of force. So yeah.
It's just not one.
And we're going to diagram this in a little bit. So we have equilibrium somewhere around here. Above the equilibrium, the weight is constant, but the restoring force is small. Below the equilibrium, the weight is constant and the restoring force is large. Make sense? So the restoring force is the force that moves something towards equilibrium. With a ball, the restoring force is a component of gravity. In fact, if you brought this somehow, if we attach this almost to the ceiling, the restoring force would be weight. And everywhere in the pendulum swing, the restoring force is a component of weight. So if I got up on the ladder and I held this up at 90 degrees or 0 degrees, then the restoring force would be weight. And here at 90 degrees, the restoring force is still a component of weight. Is there a trig function that's when it's 90, it's 0?
cosine?
That's cosine, yeah.
Subtotal.
So if you look at that angle right there, the restoring force is the cosine of that angle times the weight. If that angle is 0, then the restoring force is just the weight. If that angle is 90, what's the restoring force? Yeah, weight cosine 90 is 0. So 0. What if it's like 1 degree? Is there a restoring force? Yeah, it's just tiny because it's cosine of 1. Okay, so there you go. So we should probably talk about Hooke's law. Okay, I think that's we talked all about that stuff. Okay, so talked about equilibrium position. We talked about the restoring force. We talked about period in seconds. Talked about frequency in hertz. Amplitude. Oh wait. Okay. Now here's the thing about amplitude. Amplitude is the displacement from the equilibrium position, depending on how you want to measure it. Okay. It's the displacement from the equilibrium position. With a spring, it's very easy. Yeah.
If you're looking at like a frequency, or frequency versus time, it's the top of it to the middle, right?
Yeah. Yep. Yeah. So what he asked was, if you're looking at a graph like this, where this is 0, and then you're like versus time or versus distance, yeah, the amplitude would be right there. That's the amplitude.
Oh yeah, I remember doing this somewhere.
Yay! Okay, remember that's the amplitude. So amplitude's really easy with this. We're gonna spend a lot of time with this idea in waves next week. It's really kind of easy with springs because all you have to do is measure the displacement from the equilibrium position. Like if this, okay, let's see if I can get it to stop moving. Okay, pretend it's not moving. So if that's equilibrium position, and I move it up here, then that distance is amplitude. Okay. Or if I move it down here, that distance is amplitude. Okay. With a spring, it's easy. It's just displacement in meters. Simple. With a pendulum, it's a little more challenging because you have to specify what you're actually going to measure. Sometimes you will like to measure amplitude in angle. So if it was parallel, that would be 0 amplitude. This would be 90 degrees of amplitude, or vice versa. Maybe this is 0, this is 90. Okay. So, and sometimes you're going to want to measure distance from this point here, that distance. Okay. So sometimes you want to measure distance from here to here. Does that make sense? In this class, we're going to measure amplitude from gravity's reference point. So if this is 0, and it swings up here, this is the amplitude we care about. Does that make sense? And the reason we're going to do that, because that allows us to calculate potential energy stored in a pendulum. Cool? So right now, how much potential energy is stored in the pendulum?
None.
0. 0. If we bring it up here, how much potential energy is stored in the pendulum?
Whatever the distance.
Yeah, whatever that MGH is right there. And I know this because if I release the potential energy, that potential energy turns into what? Kinetic energy. Okay. So for this class, we're going to measure amplitude as the height from the lowest point. From here, right there. That's going to be our amplitude. That's going to be our delta H, if you will. Let's see if I can hit you. Nope. If I push this really hard, can I get her? Do it. Ugh.
If it just breaks off.
Only if the string breaks or the magnet fails. Okay. Give me a thumbs up if this makes sense to you. You're ready to move on. Okay. If you have a question, wave your hand around. I'm going to talk about some more. Wave your hand around. Good? We're good. All right. So, pendulums. So, with a pendulum, the period has a pretty cool formula. It's 2 pi radical L over G. Hang in there, Aiden. 2 pi radical L over G. That is the period of a pendulum. And I should also mention it means for small angles. the math is a little more exotic for all angles, but we're gonna focus on small angles. That means like this. That's a great example of small angles. So if the angle is like this will work. Okay. If the angle is like way huge, it doesn't work as much. We have to add another term, which I don't want to add. So the period of a pendulum depends on the length of the string, L, and the gravitational force and axon, or gravitational acceleration acts on it, G.
So, say theoretically, you said if you were to take that ball and put it to the roof, that would be a 0-degree angle, correct?
I said that, but for the purposes of what I was talking about, that would be a 90-degree angle.
If
of
it was
amplitude.
all the way to the roof?
Yeah.
Okay. 'Cause
That
I
would be
was-
90 degrees of angle from the midpoint.
Okay, because I was going to ask, if you go above that, would that go into negative numbers, or what happens then?
Wait, okay. So then that can only happen with what is called a physical pendulum, where the rod or the string, it would be a rod in your case, actually matters, and that's way beyond the scope of this course.
Okay.
So I'm going to say, don't worry about it. Yeah. So we're going to focus. In fact, it's a really good point that you brought that up. We're going to focus on pendulums where the string or the rod or the shaft or whatever device holds it to its fulcrum, the pivot point. It doesn't matter. We're going to focus on pendulums that only have mass down here. So yeah. Anyway, there you go. Okay. So what does this mean? This means if you took that pendulum and sped it up, if I give it a more oomph. So let's say we looked at the period of the pendulum. Okay. Now I'm going to give it more oomph by pulling it back even further. Is the period going to change? Okay. Take 10 seconds and convince your neighbor you're right. Is the period going to change if I bring it up here? Will the period from bigger angle differ from smaller
The
angle?
length of the string is the same.
There's no
Yeah. Yeah.
Okay, if you think the period should change, give me a thumbs up. You think the period should not change, give me a thumbs down. I'm seeing a couple thumbs up and mostly thumbs down.